Okay, so I guess we can start. Welcome, everybody. It is my pleasure today to host Jean de Terrail from OKIN, who will give us a talk about federated learning for digital histopathology. Just a very brief introduction from him. He graduated from Superlek with a degree in applied mathematics that he then used at the LHD particle generator, as well as a web startup in Geneva, after which he decided that deep learning is way too interesting and started a PhD working for a defense contractor and pioneered new automatic object detection techniques. And now he is working for OKIN. There is responsible in the field of federated learning techniques as well as biomarkers. Jean, very much looking forward to your talk. Take it away.
Thank you very much for this great introduction. Thank you very much also for having me here. So I will try to aim for a 45 minutes talk. And really my goal during this presentation is to introduce you to the world of federated learning and try to see how it can interact with digital histopathology, which you are all experts of, and try to really paint the field with coarse strokes in order to give you, in order so that at the end of the presentation, you all go out and you think you have understood something. So first of all, my presentation will not really be about trying to invent a new generic federated learning algorithm or trying to dive into a deep theoretical proof. And it will not either be about scaling federated learning to 10 to the power of 8 devices. It really will be about light introduction of FL, how can it be combined with histology, and especially what are the challenges that you encounter when you try to bring histopathology towards FL, and the practical challenges that we have encountered at OKIN when we did that, and also some open problems and ideas. And I will mention a lot of things. I will try to make it as smooth as possible, but also feel free to interrupt me at any time if something isn't clear, to ask for a clarification or anything really. Without further ado, I will now start my presentation. So my outline is in 4 parts. So the first part is really to introduce the concepts that I'm going to use in the rest of the presentation. The second part, what is specific really about histopathology data, and especially in the context of federated learning. And then I will focus on practical use case that we actually got at OKIN, so for real federated learning in the real world on histopathology data. And then I will end my talk with a few methodological advances that I think are nice to mention. And this will give us maybe the opportunity to talk a bit more about what can we do in the future to make this interaction even stronger, and to make it thrive. So first of all, clinical research and federated data access. So histology slides, as you are all aware of, are an immense source of medical knowledge that is mostly untapped because of the electronic systems of the hospitals that collect those biopsy materials, because of a lot of things about the privacy and the sensitivity about such data. But you actually get access to such kind of data when you access a database that is curated enough and with enough slides, you can actually get a lot of insights on open medical problems. So I'm going to mention 2 works that we did at OKIN on this. So we have what we called HE2 RNA, where we demonstrated that with a slide and with a proper machine learning to infer the gene expression by simply looking at the picture of the slide. So at a spatial kind of we are now able to build these heat maps where you can see the gene expression and the localization of the expression of such gene in the slide. On the right side, you can also use, yeah, please.
Yeah, so somehow your sound is breaking up. So maybe could you try to turn off the camera and then hopefully it improves. Sorry about that.
Yep. Let me try to.
Okay, let's see if it improves. Thank you.
Where did I leave, or so maybe just so yeah, just to come back on the first work. So it was about predicting gene expression from a slide and getting this visualization at the bottom left hand corner, and on the right side, predict the MSI status, and also get those nice localization heat maps. So MSI meaning microsatellite instabilities. And so really, how can we get the full power of the machine learning tooling? We need sufficient amounts of data and curated data. And in medicine, as I was saying, it's a bit harder than in other domains to actually get such data. And even if the digitization of patient data is thriving, we really need a lot of effort, such as to really build such databases with a lot of slides to be able to mine the knowledge that can be found inside. And I can mention a few initiatives like the UK Biobank, the TCGA, and now this Bigpicture initiative, which I'm sure will manage to build these curated databases with millions of slides. But the thing is, even if it would be beneficial for the models to get a lot of data, actually clinical data sharing isn't always possible, nor is it easy because of regulations that depend on the country and that can be very stringent. For instance, in France and in Europe, it's GDPR that kind of manage how the patient data is accessed and the modality under which you will be able to share it or not. And also data can be simply a private asset. And there is this nice word that coopetitive framework from Cheng, which is this kind of trade-off between, you have a lot of competitors with their own interests, and they're trying to kind of collaborate in a sense, but without sharing their data and their advantages to their competitors. And a really nice example of that, a real-world example, is a Melody project that involved 10 pharmaceutical groups that each of the pharmaceutical group has its own task, but they still benefit from the sharing of the knowledge, but not the sharing of the data. So through this federated network, we will be able to share some information that will help the machine learning models to be better, but without exposing the underlying data. And it is especially true for rare diseases, where it's actually very hard to get to this critical mass where you will be able to have nice machine learning models working. Because if you have only, like, say, 100 slides, then you force, in some cases, you cannot meet the barrier that is necessary to get the models to really extract knowledge from your slides. So for all those reasons, was a new technique was introduced, so this collaborative federated learning framework, and I'm going to go into the next few slides about exactly what it is and what it means in practice. So the old paradigm about training machine learning models was about pulling all the data into one center with possibly multiple servers. But all the data was in one place. And now the new paradigm with FL is that bring the model to the data, keep the data on the premises of the hospitals or the medical institutions that you are partnering with, and you only exchange the models in between centers. And how does that sharing actually take place? If you take a bit of a more zoomed in view on exactly what's going on. So it's actually very simple. So the naive version of federated learning is just iterative training. So sorry. So this iterative training is about doing local training on your centers and then synchronizing the models in a repeated fashion in a central server. So you can see it with the arrows on the right side. So the model goes back and forth between the centers where it undergoes a local training and the averaging in the center of the model. Is it clear for everybody? I apologize for the noise. Okay, I'm going to assume it's clear and go to the next slide. So it's important to understand that in federated learning, there are two settings that are very different. So the first one is cross-device FL. So it's about training with a lot of devices, so millions of devices, and it's a use case that was invented for institutions like Google that wanted to train machine learning models on a lot of smartphones. And the local data sets in this setting are very small. If you put it in perspective with the total aggregated data present on all the smartphones. On the other hand, the setting that we are the most interested in at Aokin is what we call the cross-silo FL, where the number of participants is limited. So let's say 2 to 50 participants is what you would end up with, so because each participant is now not a smartphone, but a hospital. And some technical parts actually change. So all the participants can actually be there at all rounds, because unlike smartphones, hospitals don't turn on and off. And you can assume there is a good bandwidth, and the local datasets are large enough. And the use cases that you encounter in cross-silo are healthcare, insurance, or industry. So now I have finished the first part about exposing the general principles behind FL. And then now I'm going to go deeper into histopathology data and the specificities of such data in the context of FL. So FL has actually four main kind of challenges. So the first kind of challenge is, can we federate any machine learning models? So usually the hypothesis about FL is that the models can be trained with what is called gradient. So it's just a technique to train models, but some of the models don't actually use the same kind of technique, so the federation is a bit less trivial. There is a privacy challenge that is especially important. So because we communicate models, the models can actually leak something about the underlying data, because the models are trained on the data of the patient. So it means that some of the knowledge of the data of the patient gets embedded into the model somehow. There are the communication challenges as well. How to reduce the communication costs and limiting the number of exchange rounds. as a consequence, we limit the privacy leakage of the model. And there is the heterogeneity problem. So what is the heterogeneity issue? Is the differences from center to center in terms of their data. And I'm going to come back on that on the next few slides. So I have a bit of a technical slide just to get back on some mathematical definition, but it will be helpful for the future. So most of machine learning in general follows what we call ERM, which is empirical risk minimization, which assumes that the data is IID, so independent and identically distributed. So it means they assume that the data in the label, the generation process, is the same across all centers. And of course, you all know that in healthcare, in general, it is not the case. You can maybe use this hypothesis intra-center, but the distribution from each center are different in between centers. And when you take a deeper look at this as such changes, there can be both a feature shift and a concept shift. So what is called the feature shift in the literature is really the generation process of the X's. So X, in our case, means the histology slides. So the generation process of the histology slides is not the same from one center to another. And for histopathology, it's really an evidence for experts that PI is not the same from center to center, because it can be influenced by a variety of things, such as staining, scanners, resolution, depth, physical conditions, the amount of staining, the conservation, the fixative, and a lot of such things. And you can also have what is called a concept dist shift. Is if the generation process from the slide to the target of interest, Y, can be different in the center. So it would mean that your population, the medical problem is not exactly the same from one center to another center. So what could be the sources of such heterogeneity? So I already hinted at some in my previous slide. So it could be the demographics that would change from one center to another. It could be the biopsy prep and the staining. It could be the digitization process. And it could be also the cohort selection, the PI, and also more basic issue about the format of the data and the conventions and annotations used. Even if there are some nice initiatives to harmonize the data in healthcare, we are not there to a state where the format of all data is the same in all the hospitals, and especially for histopathology. So when we take a deeper look at the statistical shifts that can happen for histopathology, so for instance, if you take the Chameleon 16 dataset, which is an open source database with 2 centers, you can see that if you look at the color histograms of the distribution are widely different from one center to another. And this can cause actually issues in the training of your model, because in federated learning, you usually train one global model. And because of the differences in colors, it will actually make the training harder for the model. And it may negatively affect the performances of your model. Is there any question at this point? Nope. Again, don't hesitate to interrupt me. So how can we go about taming these feature shifts that we encounter in histopathology? So one possible way would be to try normalizing the data. So normalizing the data is aligning the distribution, so P of X, to a certain template. So it can mean a lot of things. So for instance, on the far left, if you take a look at one-dimensional kind of data, you can take distribution on the left and align it to the template that is a Gaussian. So So in histopathology, it usually is about the staining, because the staining is the most visible artifact that you can see when you look at an histopathology slide. So there are a lot of traditional computer vision techniques that can be applied, and techniques that are specific to the histopathology domain and how the hematoxylin and eosin staining or other kind of staining will affect the process of light going through the slide and giving a specific color to a specific cells or tissues. On the right side, you can see a recent approach called cycle GAN, which take an image from a model and tries to transfer it to another model. So the visual results look appealing, and you can see that with such a technique, you can achieve this kind of normalization, when normalization is seen as a transfer of data towards a template that could be a specific domain or distribution. If we take a deeper look at normalization methods, one possible overview of normalization will be to split normalization in two, where we have data normalization on the left side, where we will actually normalize the data. So we will generate X primes. So in the case of histopathology, we will generate new slides, a bit like the picture that I showed you. And then we will train a model on the X prime. And on the other hand, there is model normalization, where you leave the model to actually perform this normalization task in some kind of implicit fashion. So there are highlights and downsides about the two approaches, really. One cannot say that one is better than the other. Data normalization, it's more interpretable because you can actually see what kind of normalization is taking place. It's more aesthetically pleasing as well because it's a human form kind of data, but also it's purely offline, which means that you have to actually normalize the data once towards a domain. And when you encounter a new domain, you actually have to retrain your normalization pipeline and reproduce the data on disk. And when you look at model normalization, it's less interpretable because the normalization happens inside the model, but it's more flexible because it doesn't really depend on a specific domain. It's more generic because it can adapt and it's online. So example of both methods includes GANs, style transfer, and I don't know if you have seen the recent craze about dream boost and diffusion kind of models, where then I'm encouraging you to check it out because it's really funny and it's interesting to see that machine learning could perform so well given enough internet samples of and for model normalization, one crucial example would be batch normalization. And now I'm going to go into the part 3 of my talk if you don't have any question. So I'm going to present in part 3.
I see. I see there's a hand raised indeed. Please.
Yes. So my question regarding data normalization is, when you are trying to transfer it to some other style, let's say you are using cycle GAN, how do you decide that what is the domain A and what is the domain B? Because here in this case, all the clients, they cannot share the data themselves, right? So how do you tackle that domain shift?
You have a perfectly valid point, and it's actually quite a huge problem. What is the template or the model we should target in the case of a federated network? And it's not easy. So there is some technique that tries to remove the influence of the staining altogether, which going to create some kind of common template. But in FL, we could choose, like, for instance, the domain of the center, the first center to join the federated network. But why would this domain be better than really? I'm going to be frank, it's an open question. Which model should be chosen for this normalization?
Yeah. But if you, let's say, choose the first domain or the first client as the target domain or the template domain, to train a cycle GAN, you still need all that data, because there will be you will be training the model. So, but you cannot share the data between the other nodes, right? So how do you do that? How do you train such a model then?
So again, perfectly good points. So one idea would be to get the information of the staining used in such center that is chosen as a template, and then use a nationwide open source database to actually train your model. Or you can go to a more complicated kind of technique, but that is still open research.
Thank you so much.
There's a second question.
Yes, hi, I have a question as well. Could you tell us which is the one that you use if you use one of them and not both, and why?
So actually at Aokin we have a lot of different projects about histopathology, and we don't currently have a one-size-fits-all approach. Really, it depends heavily on the cancer. It depends heavily on the kind of model. We have experimented with a lot of such techniques. So most traditional computer vision techniques such as Reinhardt, Masenko, Varadane. And we also have experimented with cycle GAN kind of approaches. I think they are all mostly the same. I think there is a slight advantage that we have seen for the Varadane kind of method, but again, it's heavily problem specific.
Okay, thank you.
Okay, so now I'm going to be able to present you one of the real-world works that we have done for federated learning for histopathology. So it is unpublished work. And it's really one of the very few applications that you will be able to actually see for histopathology doing federated learning in the real world. Meaning we are not simulating fake centers, or we are not redistributing the data into the original centers in a post-hoc kind of fashion. So this project was done in the scope of an initiative with public and private actors called HealthChain. And the open question that we had was about triple-negative breast cancers and how they respond to neoadjuvant chemotherapy. So actually, it's an open question now. When you do a biopsy at the diagnostic, then all patients mostly undergo neoadjuvant chemotherapy, so chemotherapy that is prior to the surgery, because on this cancer, all the hormonal kind of treatments actually fail, and you don't know in advance if the patient is going to answer or not to your treatment. So we are trying to predict what is going to be the treatment effect on a new patient. So if we had the perfect model, we could really use in clinical practice, because if we know the patient is going to respond well to neoadjuvant chemotherapy, because it's toxic to the heart, we could even envision therapeutic de-escalade, so giving a lighter treatment on the patient. Because if it's going to work very, very well, maybe giving less toxic kind of treatment to the patient will work as well. Or if we already know it's not going to work, we're going to gain time and orient the patient towards more experimental kind of treatment. And gain of time in cancer, it can really mean more luck in terms of survival and relapse outcomes. So it's really important. So if we use what is called the residual cancer burden to measure after the treatment, so 6 months afterwards, how much tumor is there on the slide. So the formula is important. It's just a way to measure the amount of tumor that is still present on the slide after the chemotherapy. And so if there is a lot of tumor still on the slide, then we say there is no response. And if there is zero tumor in terms of residual cancer burden, we say there is a complete response. In machine learning, we call that a binary classification task. So the challenge is, can we actually solve this task? And for a new patient, so given its diagnostic slide, be able to infer whether or not in 6 months, if we give the patient the treatment, there will be a complete response or not. And so this is what we did with Institut Curie and Centre Léon Bérard, which are 2 French comprehensive cancer centers. And we actually deployed a federated network based on our open source backend called Substrat, where you have this setup where data stays on the premises of the hospitals, but models travel. And at no step in this project, the data was pooled and we redistributed it in the centers. The data stayed on the premises for the whole project and even afterwards. Because simply in terms of regulations, you can't pool the data because it's too sensitive. And so you can see that there is an imbalance in terms of number of patients inside both centers. And so we trained a machine learning model directly on whole slide images. And the challenges of histopathology data for machine learning, so I'm going to go over it quite fast, but it's the important size of the images, so it doesn't fit in your RAM. You actually have to extract the matter and tile it to get from a slide a bag of features. And then you have to classify such bags of features, so you have to come up with an aggregation module on which you can plug a machine learning model to predict the outcome, so 0 or 1, whether or not the patient is going to respond well to the treatment or not. And so what we observe, so on real data, first of all, when we take a look, we forget histopathology slides, and we take a look at only clinical data. So in this case, it was a grade, and the tumor lymphocytes infiltrate in a percentage that was measured. So this is a histological kind of measure that was derived from the raw slide from pathologist experts. So if we use such X's, we can actually predict up to 70% AUC more or less in one center and up to 55 for the other center. So you can already see that there seems to be a difference in between the cohort in the real world. So it seems even when using such structured data, there is a distribution shift. So the medical problem is not the same exactly in both centers. If you use deep learning, you can actually match and even in some cases outperform what you have using the clinical data. And this is really rare, actually, that you can do that, because the information present in histopathology slide is a lot less structured. And thanks to the federated network, we can transfer the model trained, for instance, on Centre Léon Bérard on Curie, and we can see that it performs the same that a locally trained model. So a model trained on Curie and tested on Curie. It's approximately the same kind of performances. So it's a good sign that federated learning will work, because the distribution in terms of histopathology data are not too different. And actually, so this is what I was saying. So this calls for the use of federated learning. And actually, when you use federated learning kind of strategies, you can get even better performances. And what is really interesting is that in this setting, you're actually using one model and not one model per center. And you take a look at the worst case scenario for your model. You take a look at intra-center performance. So you compare it with a model that is trained on Centre Léon Bérard, and query. So what would be even more interesting is to have external validation to actually confirm if the fact of adding another center was actually beneficial for the model. And actually, what is really nice with this kind of aggregation module that we're using is that we are able to extract what tiles are actually important and what tiles are associated and what kind of specific histological patterns are associated with either a positive answer, a positive response from the patient, or a negative response. And for instance, so I'm not going to go over all those because I'm not a pathologist, but for instance, tumor infiltrating lymphocytes was already a clinical variable that was of interest and that was known to be associated with the response. And the federated learning model actually rediscovered this association without us telling it especially to focus on such pattern. So really the takeaways, so FL can actually be deployed in the real world and on histopathology data as well. Using data from multiple sources can bring better performances than using only siloed data. And of course, machine learning for histopathology data is useful for cancer research. Do we have any questions? Sorry, I got to go a bit fast.
That's
but
okay.
I want to keep some time for the last part.
So let's wait very
No
briefly. If no one has one, I have one. Oh no, there is someone. Let me just quickly see. Magdalena, go ahead.
Hi. So my question would be, in this setup, the federated learning setup, does the AI developer need to see the data that they are using for the model training? You mentioned several times that the data stays in the hospital, but is it viewable to the developer, or does it need to be?
So you actually have a very good point. So on some projects, the specificities of the projects make it so that you have to be blind. But of course, you all know that in machine learning, it's a bit of an iterative process, and you kind of have to debug your model. Like for instance, see if the tiling was properly done, if the matter was extracted, or if you don't understand the results or the performances, it's nice to have some tiles to visually inspect. So we partnered with the people inside the hospitals, so with data engineers and doctors, and we had this kind of back and forth with them, but it was actually very useful to not be completely blind to what was going on and to be able to do some data extraction at some point to actually see what was going on. But in some projects, like Melody, it was 100% blind for the AI developers. So it would depend really on the situation. Of course, if you are in a context where you can do non-blind federated learning, it's much better and much simpler.
Thanks. Abbas, does that also answer your question? Next, James is asking, thank you. Do you need the data in common data model, GOMOP? How much benefit is it if data has been put in common data format?
So the benefit is actually immense. So we actually had to work with data engineers from all the centers to do this harmonization step, because if we had plugged ourselves directly on the raw data sources, we wouldn't have been able to match the column. So because of the lack of standard, because OMOP and FIRE and all this kind of thing is not actually deployed onto every center, you have to have this manual kind of step with the data engineers on premises.
Thanks. Did you compare the federated learning models with transfer learning, i.e. use a model that is pre-trained on one center to fine-tune the data from another center?
So I actually, full disclosure, in our pipeline for the feature extraction, we use a pre-trained data. And we compare it with ensemble of model, which is a strategy, and with local. So it's not per se fine-tuning, but it's even more than fine-tuning. It's starting from a network that was, in this case, trained on ImageNet, training locally, and we compare with this local model. But of course, you can envision a lot of strategies, such as cyclic learning, where you have one model, you train on one center, and then you give it to the next center. The center fine-tunes it, and then it passes on to the next center, and so forth.
I would have a question, and that is, so you mentioned Melody more than once, right? And Melody was, of course, a project very big, very many partners, that if I describe it, didn't actually show that great an improvement in the models. And now you have a very small one that actually shows a very nice improvement. What do you think the necessary setup should be to see this sort of synergy between partners?
So, okay, thanks for the great question. I think really it's a bit philosophical, so I will give my very biased point of view. But I think with such a kind of federated learning, we are still learning. It's really dependent on the problem, but from all the projects we participated in, we actually understood that it was even better not to be blind, and we had to do a lot of back and forth, and to have some people in the center that help us to understand what's going on. And there is a lot of preparation works that is necessary for federated learning to actually work in the real world. And this preparatory work, so it can be cumbersome, of course, if you scale the number of centers. Harmonization becomes even more difficult. Maybe the intersection of the variables that are present on each center is not the same. And of course, if you have a small number of centers, it's simpler in a way. But really, it depends on the problem. But for instance, in a total blind fashion, you can have a partner that incorrectly normalizes the slides, and you wouldn't know it because it would be blind. Yep. And so you have to kind of find a trade-off between those kind of two modes. We call it remote access and remote execution in our internal slang.
Okay. Another question from Bidohashi. In case of transfer learning, let's say you trained a model in center 1 and 2 and then apply it in center 3, but you never use center 3 for training. What kind of normalization do you have to do so that works? Or does it work at all?
So actually, I mean, I can hide myself because under the it depends on the problem. Sometimes it doesn't, right? But in this project, this is a very specific one that I just presented you. We actually showed that it does transfer to stainings and scanners that it hasn't seen. But we at Aoki, we are also developing what we call diagnostic tools, which are going to be what is called in French marquage CE, which is some kind of organization that approves that the model can be used in the prospective world, so on actual new patients. And on this process, you have to validate your performance on a specific kind of scanner, on a specific kind of staining, and you cannot claim that your model will magically transfer to any kind of new scanner type.
Yeah. Thanks. Ivana, I'm sorry, I think I had been left you hanging with your question for a bit. Your turn.
Hi, no worries, no worries. One last question is, how far is it from these models being used in everyday clinical practice in these two specific centers?
So I think so. I'm not gonna lie. So we are not there yet. But so you know, you can always
approximately how far.
I mean, for this kind of think histopathology may be not a sufficient source of information to really being able to predict accurately if a patient is going to answer or not to the chemotherapy. I think you would have to go to more modalities that are more granular, like genomics, to really showcase and to really understand what's going on. I think we do not understand yet exactly what's going on for such patients. But of course, TILS annotation is an expensive process, and if we can help the pathologist with some kind of semi-automated tool, it's even better. And I think that a lot of work actually tries to detect TILS directly on histopathology slides, and it's actually a much simpler problem, but it actually works.
Yeah, it makes sense. Thanks for your answer.
Maybe I don't know if I have some time for a bit of part 4. What do you think?
Couple of minutes, sure, yep.
So I'm just going to go over very quickly. I think I'm going to skip the technical heavy part about batch normalization, but I'm encouraging you to check out our work, so siloed federated learning for multicentric histopathology datasets, just because it's an example of a methodological work that looks at implementing normalization inside the model, that answers one of your former questions: how can we make sure that it transfers to another domain that is unseen? And so I don't have time to go into the details of such slides, but I send the slides to the organizers. And of course, if you have questions, we are more than willing to answer that. So I'm going to gloss over that and go to the second part really quickly, just to introduce a new open source database that we just open sourced, and that will be presented at URIT actually next week, which is a conference about machine learning. And really, we wanted to answer a need. Why are we doing this methodological work at Hawkin? Because it can give us a sense on how hard it will be when we do it in the real world. Actually, federated networks are hard to set up. You have seen that there is a lot of preparation works going on. And what I didn't talk about, but there is a lot of legal and IT setup as well, which takes a long time. So you have to have a playground to simulate FL before you can go into practice. If you do cross-device, so if you do smartphones, you actually have a lot of playgrounds. So you have Leaf, that is the main one, and then you have a lot of others. But when you look at cross-silo, often what is done to create fake clients is to separate by labels. So one client ends up with all the label 5, one client with all the label 6, and it's really not representative of the real world, right? And the heterogeneity is that you can find in practice in the case of histopathology. So there is a mismatch between theory and practice. So now we introduce FLAMB to bridge the gap between researchers and practitioners in cross-silo FL. And it's an open source dataset suite with federated learning data that is real world in the sense where it's not deployed real world, so it's not behind hospitals' firewalls. We actually resurface the centers, the original centers where the data was coming from originally in some datasets that were accessible. So for instance, the Chameleon 16 dataset that I mentioned on the left for histopathology. And actually, so the centers that we use are actual centers. So the heterogeneity that you can play with is the heterogeneity that you're going to encounter into the real world. And so you can develop new fancy normalization techniques with a cycle GAN training without exposing the data, as one of the previous questions hinted at, or some federated learning strategy. And really, we have all these Python building blocks that would allow you to do what you want in this playground, change the dataset. So of course, we don't only have histopathology, we have a lot of things. And you can quickly change what you want, and you can use Substrat as well, or other Python federated learning frameworks. And you can play around and do a lot of So I don't know if you're familiar with personalization. That goes away from the paradigm where you have one global model. Now you will train globally, but you will have one model per center. So maybe it's one of the answers to the problem that was mentioned. Or you can use privacy techniques on the gradients, such as differential privacy, where you make sure that the gradients cannot be retro-engineered by an ominous, malicious adversary with a lot of knowledge. And it's actually open source, and we welcome contributions and we welcome discussions on this benchmark. And I really think this is with such kind of playgrounds that researchers can answer the philosophical questions. How hard will it be? I mean, it's a part of the answer, but we need to first develop some theoretical tools before jumping into the real world, because it can be hard. And I'm stopping here to get questions.
Yes, thank you for the presentation. I have a question about the security, mainly for the weight sharing. What do you recommend? The encryption homomorphic, the SMPC mechanism? What is the best solution?
So again, there is no best solution. It depends on the situation. For Melody, we used SMPC. Okay. So I think realistically, SMPC techniques are the best ones because when you do a neural network training on encrypted data, so when you go like fully homomorphic, it's still too time consuming, and you have too many rounds to just do one gradient step. Mm-hmm. And so yes. I think they are not just developed enough, but SMPC, in another hand, are techniques that are not easy to implement, but that are faster and that can be applied to projects in the real world.
Okay, yes, perfect. Okay, thank you.
Thank you very much. Any last question? Three, two, one. Okay, in this case, I thank the speaker. Rick, any last words?
Yeah, also from my end, thanks Jean for providing this great overview, and thanks Holger also for chairing the session. Yeah, it was already mentioned in the chat. The session is recorded. Will be shared on the Bigpicture SharePoint. If you don't have access, you can email us, and we will make sure you get access. The next webinar will be on December 5th on the NPIC project, so on digitizing the UK pathology worlds, provided by Darren Trenner from Leeds. So you're all very much invited to join that session. Also, if you would like to share your work to the Bigpicture community, please reach out to us, and we'll see if we can provide you with a slot to share your work with this group. Those were my last words. Thank you all for joining, and hope to see you next time.
Thank you very much.